Hi Kamesh. So we'll start for a few more minutes and then we'll start. Good evening. Hello, good evening. Can you hear me? Okay. Let's start today's session. So you have mailed me these questions, right? So first we'll solve this. Start to solving with this question today. So yeah. So this is the question number 31 of GATE 2021. So the question is, in the absence of any external stress, which one of the following statements related to the interaction of point defects and the dislocation is false? So to solve this question, we'll go step by step. Okay. So first we'll see option A. So in option A, what happened? What is it is mentioned that an oversized solute atom would preferentially migrate below the slip plane of an edge dislocation. So do you know when we dissolve a oversized solute atom in the matrix, what kind of stress is developed in the matrix? What kind of stress it will form in the matrix? Like let's say you have sorry. So let's say you have this set of atoms initially. Okay. Now if you uh, put one oversized atom here, then what kind of stress it will develop in the matrix? Yes, exactly. So as you can see from this diagram, like, is the next slide is visible? Yeah, now it is visible, right? Ah. So as you can see from this diagram, it these are the regular size of the atoms in the matrix which you have. Now one oversized atoms is dissolved here. So this is a yeah. So this is a one oversized atom that is dissolved here. So because of this oversized atom, it is basically uh, ex- developing compressive stress surrounding to this surrounding its area. So because of this and similarly if you put one small size atoms whose size is less than the size of the atoms which you have in the matrix, it will form uh, tensile stress. So so in this case it will form compressive. Okay, and this case it will form tensile. Now let us see what is the environment there in the surroundings of an edge dislocation. So if you see an edge dislocation, uh, in this case, this is edge dislocation, the location of the line of the edge dislocation, right? Now if you see the arrangements of the atom at the top part and the bottom part, what you will find that in the top part, so there because of the and the bottom part, because of the absence of the atoms in the ha- in the bottom half plane, because of that the matrix will get strained in that direction. So that means this atom is get basically it pulls towards this region, this set of atoms. So that means this that at the bottom half of your edge dislocations, it is under tension or it is under tensile stress. Okay, similarly at the top half of the edge dislocation, it is under compression. Okay, so now so this if you now put an oversized atom, okay, which basically develops a compressive stress surrounding these atoms. So now if you these atoms if you put in this nearer edge dislocation, so what will be the tendency, like at which location it will try to go? Seeing this diagram, I think yes, you can also answer it. Okay, so now as this region is under tension at the down half or the bottom half of the your edge dislocations, so now if you put an large substitutional solute atom, so as it creates a compressive strain surrounding its area, so it will try to go at the region where the atoms are in tension, so that relaxation will happen. Similarly, if you put a small substitutional atom, let's say in this case this one, so it the surrounding to these atoms, the atoms are basically in the tensile stress. So this atom will try to go in such a location where it will find out that where the atoms are in the in compression. So if these atoms goes there in the top half, so it will also the luxation of the matrix will occur. So this all these things are just to minimize the energy of that near the dislocation area. So now you have right. So this one is the option A is true or false. Yes. So this is true. Now, now we'll look for the option B. So option B is basically saying a spherically symmetric point defect can interact with both the hydrostatic and shear stress field of a dislocation. Okay. So spherically symmetric means what? Like you have a solid atom which is exactly spherical in shape. Okay. So now even here if you can see if it is exactly spherical in shape, so it will distort the matrix in all the ways in a similar fashion. Okay, in the x y or in the if it is like this is in the 2D drawing is there. Now if you imagine in the three-dimensional space also, if you put one atom in the all the surroundings area will be distorted in the similar fashion. Okay, so that is basically that's why it is mentioned that spherically symmetric. So spherically symmetric point defects. So if you insert any spherically solid atom, so it will distort the matrix in all the direction in the similar fashion. So that's why in the at the surrounding area it will only develop the hydrostatic component of your stress. Like in the three dimension, if you see, you have sigma xx here, sigma yy, and sigma zz. It will not create any kind of shear components as it is distorting the matrix in a similar all the direction it is distorting the matrix in the similar fashion. Okay, so that means if you insert a spherically symmetric point defects, it will only have the hydrostatic component of the stress. Now here it is mentioned that this hydrostatic component of the stress, it can interact with both the hydrostatic and shear stress field of a dislocation. So if you see the stress field near a edge dislocation or near a screw dislocation, you will find that. So this is the stress field near a edge dislocation. So you can see that here hydrostatic components are there, and also in the xy plane the shear components are there. So basically it is a plane stress condition. And if you see the stress field near a screw dislocation because of a screw dislocation, so you can see that no hydrostatic components are there. Okay, only the shear components are there. Okay, so now you have a solid atom. So solid atom, it is creating a stress field like this: sigma x, sigma yy, and sigma zz. All the shear components are zero because it will create a pure uh, hydrostatic stress in your. So this is for sigma of your solid atom. So now from this you can say like in which dislocation it will interact your solid atom. Which dislocation it will interact? Will it interact with screw or will it interact with edge dislocation? No, it will not interact with screw dislocation. As you can see here, it has only the hydrostatic component of your stress. But in case of your screw dislocation, there is no hydrostatic component of your stress is there. So how it can interact with the screw dislocation? It cannot interact with the screw dislocation, as screw dislocation doesn't have any hydrostatic component of the stress field. It only have the shear component of the stress field. So the solid atom never interact with your screw dislocation. But if you see the edge dislocation, it has if you see the edge dislocation, it has the hydrostatic components of your stress field. Okay, so in this case, your solid atom can interact with the edge dislocation, but it cannot interact with the your screw dislocation. So, as mentioned in this option, it was mentioned that the spherically symmetric point defects can interact with both the hydrostatic and shear stress field, which is not true, right? Because a spherically symmetric point defect, it will develop a stress field which is pure hydrostatic in nature. So it cannot interact with your shear stress field. It can interact only with the hydrostatic stress field. So this statement is false. Okay. Now we'll see the option C. Okay, so option C is it is mentioned that a point defect can locally modify the elastic modulus and thereby can change the interaction energy. So it is basically saying that let's say this is your matrix. So this is your matrix. So now you have one solute atom here. So it is basically mentioned that as the presence of this solute atom here, it is basically locally modifying your modulus of your matrix. Or so and because of that it also changes the interaction energy. So let us find out whether it is true or false. Okay, so now what is the how the energy of a dislocation is you can write like so basically in the very simple term, if you will find that energy of any dislocation, either it is screw or edge, the energy of a dislocation is proportional to the g into b square. So g is the your modulus of the matrix or nearby area of that your dislocations, and b is basically Burgers vector. So this is the energy of dislocation. So in case of screws and edge dislocation, some other terms will be there like new and all these things. So now this is not the concern in our case now. So in our case, it is mentioned that as this solid atom, it is locally modifying your modulus. Basically, it is mentioning it is locally modifying your G. So if it is locally modifying your G, so that means let's say in this case, let's say this atom in this case it is not a effect of a size. In this case it is a effect of the modulus of your atom. So let's say this is your arrangements of your atoms near the matrix. Okay, so here I am putting one another kind of atom. Okay, so let's say this atom is relatively softer than matrix atom. Similarly, let us put one more atom, let's say here. Okay, we can extend this matrix a bit. Okay, so let's say we are putting one more atom here. Here this atom is relatively harder. Okay, so now it doesn't matter if let's say the size of the both of the atoms are same. Okay, the size is not different, the size is same. So in this case it is a little bit harder and it is little bit softer. Okay, so in this case your modulus, that G value will be less. Let's say G of matrix is this Gm, and this is, let's say, solute to atom 1 and this is atom 2. So for atom 1 your G will be sorry, atom 1 this is will be the less like G of your atom 1 nearby this area of the atom 1, G will be less than your G of the matrix. So now if here the G is less, so now if you have some dislocation nearby, like let's say here you have one dislocation line. So let's say these atoms, these planes are not there. So let's say this is a dislocation line. Okay, this is a half plane of your dislocation where this half plane is not there. So now, so in near this area your G is less than your matrix. That means near this area it will be Gm because near, no solute atom is there. So here your G will be locally, it will modify the G of your matrix. So now here this location, at location 1 it will be G1, and at location 2 it will be G2. So this will be the relations between the G2, Gm and G1. Okay, so now okay, okay, so now if your dislocations moves in this near these points, or let's say the atom is moving these points, anything is fine. So what will be the then the your energy of the dislocation? Earlier your energy was proportional to Gm b square. Now if atom 1 moves to this location, or this location moves to near this atom, your energy will be proportional to G1 b square. And now if this dislocation moves near this atom, what will be the energy? The energy will be G2 b square. So which one is larger? Let's say this is U1, E2 and E3. Which energy is larger? As G2 is larger, so energy 3 is greater than energy 1 and then energy 2. So this will be the lessons, right? So now that means what? Always any system tries to uh, decrease its energy. It never try to increase its energy. So that means so most preferable condition is which one? E2. Okay. So in other way, we can tell that this dislocation will get attracted by the solid atom, which is relatively softer than your matrix. Okay, and in the other hand, you can say also that this dislocation will get repelled from this atom, which is a relatively harder than your matrix. So that means basically your whether the dislocation will get interacted towards your solid atom or it will get repelled from your solid atom. That is depending on the modulus of your that solid atom. So this what is mentioned here, this is true. Basically, any point defects or any solid atom, it can locally modify the elastic modulus, and as the elastic modulus is getting modified, that interaction with the dislocations it also getting changes. That interaction energy it is also getting changed. So this statement is true. Understood? Okay. So now option D, we'll see the option D. Option D is vacancies are attracted towards the compressive region of a dislocations. So what does the vacancy? What is means by vacancy? Vacancy means there is no atoms or like it is a vacant spot. No atoms is there. So now if you see at dislocations, so there are already some vacant spots are there. What happened? Okay. Hmm. So if you see these locations already vacant spots are there. That means extra the atoms in the bottom half of your extra half plane that is missing. So if any other vacancy, let's say this is one more vacancy is there. So what it will try? How it cannot go to this location because already these locations are vacant. Okay, and also the vacancy. So it will try to go to the this location where you have the extra half plane of atoms is there. So as the extra half planes of atoms are there, so this vacancy can will try to go this location, and which is the compressive region of your edge dislocation, not the tensile region. Because at the tensile region, already you have vacant spots of your atoms. Like already it contains the vacancy. There are no atoms are there. So whenever you have vacancy, it will try to go at the top part or the above part of the top part of the your edge dislocation, which is under compressions. So yes, so here also in the option D it is mentioned that vacancies are attracted towards the compressive region of your dislocations. So that is also true. Okay. So then correct answer is it was asked which one is false among these statements. So the correct answer is option B. Is it clear now? Okay. So in order to solve this type of question, you have to visualize a little bit. Like if you go through the statement by statement, then it will be easier for you. First you will see whether the first statement it is correct or not. You have to visualize a bit more. Like in this case we first saw what is the effect of oversized solute atom of the matrix. Okay, first we saw this one, and then we saw how the edge dislocation affect the matrix. Okay, so first we saw how the solute atom is affecting the matrix, then we saw how the your edge dislocation is affecting the matrix, then we found out the oversized solute atom it creates a compressive stress near the matrix, and in case of dislocations at the bottom half plane it creates tensile region, at the top half plane it is creating compression region. So in order to relax for the relaxation of the matrix, obviously this oversized solid atom try to go in the region where the tensile where the matrix are in the tension, so that it can relax the stress, relaxation of the matrix will occur. So this way you have to just visualize the thing and you can approach this type kind of questions. Now one more similar question I have, that is from GATE 2018. This is the question number 37 of GATE 2018. So The question is, consider a dilute substitutional solid solution of X in a metal A. Okay, so that means in a metal A, you are adding some atoms of your X atom. Okay, so now the powder diffraction pattern of this alloy reveals that all the peaks have shifted to the left when compared to those of pure A. So first, you have measured one XRD pattern for pure A. So let's say the peak was like this. So I'm just writing randomly. Okay. Uh, so now after addition of the your X element in with metal A, now it is mentioned that your peaks are shifted little bit left. So earlier location was this one, right? Now all the peaks have been shifted a little bit left. So that means now your peak distribution will be something like this. Okay, so it will be something like this. So now uh, if such solute interacts and segregate to an edge dislocation, which one of the following position around the dislocation will it preferentially occupy? So here it is basically same type of question it is there. It is mentioned you are adding X type of atom with your pure A matrix. Now because of the addition of that X atom, it shifts the XRD peaks towards the left. Now it is asked that if there is a edge dislocation nearby, so preferentially which location of the edge dislocation it will occupy. So will it occupy these locations, or this one, or this one, or this one? Okay, so now we have already covered this concept. So can you approach this question, how to solve this, what will be the correct answer, and why? All the informations are given. So first approach, what should be the first approach, what you should know here in order to tell at which location is preferential. So as we have covered from that in the previous question, so there we know from that question we have got idea. If your atom X atom, if it is oversized, it will go to the bottom of the dislocation line. If if it small or undersized, it will go to the top region. Okay, so this you know. So in the option A, that X atom goes to the top side. In the option B, it is basically at the dislocation line itself. Means not dislocation line, at the same plane of this where the dislocation are present. And here it is also at the right side of the dislocations, these lines or that plane. And it is here it went to the bottom. Okay. So now in order to solve this thing, what should you want to know first? Yes, size of the solute atom. So whether it is oversized or undersized, okay. But in this question, it is not directly mentioned. Okay, it is not directly told that whether the X atom size of X atom is it greater than A, or it is greater than less than A. Okay, but it is mentioned. It is this information is also given, but in some tricky way, right? So this line, if you see the powder diffraction pattern of this alloy reveals that the peaks have shifted to the left when compared to the those of pure A. So from this statement you can find out whether the size of your X atom, whether it is oversized atom or whether it is undersized atom. So now the peak is shifting, like what is the exact peak in the X direction it is intensity, and sorry, in the Y direction it is intensity, in the X direction it is theta. Okay, intensity versus 2 theta. So peak is shifting in the left side means what? Your theta is decreasing, right? So theta is decreasing means what? If you see the Bragg's law, n lambda is equal to 2d sine theta, right? So if you see this one, n lambda is 2d sine theta. Now, theta is basically decreasing, right? It is mentioned that theta is decreasing because peak is shifting to the left. So why, if theta is decreasing, how your d will vary and how your lattice parameter will vary? Tell me. So d is basically n lambda by 2 sine theta, and d is related to lattice parameter by a by root over of a square plus k square plus l square equal to n lambda by 2 sine theta. Now d increases, a also increases. Yes, right. So as theta is decreases, so your d also will increases and your a is also increases. So now tell me, if what does it means when you are adding some atom, your a is increasing. So what does it means? Size of the atom is larger or lesser? If your lattice parameter is increases means what? Size of your atom is larger or lesser? Yes, exactly. So as your lattice parameter is increasing means it is giving you the hint that the size of the X atom, which we are adding with the A metal matrix, so that size of your X atom is larger than your size of the your A atoms. That's why your lattice parameter is increasing, and that is getting reflected from the XRD diagram or XRD pattern. Okay, so that information was not directly given to us. So, but in some tricky way it was given to us. So now we have found out so whether the size of the X atom is larger or it is lesser. So as the size of the X atom is larger than your A atom, so that means this is the conditions. So that means X is oversized than the A atom. So now we know that it will preferentially occupy the bottom positions of your age dislocation, where the atoms is under tension. So what will be the correct answer then? Now we can answer it. Yes, exactly. So that this location will be uh, preferential location for this X atom. So correct answer will be option D. Okay. So this type of question you will find in several different kind of ways. Like first one here is that it was like true or false kind of questions, or in the form of true or false statement it was given. Now it was given in the form of all that some diagram was given, and also that whether the atom is oversized or undersized, that was also not directly given to you. So for this question you have to think a little bit and then you can answer it easily. Okay, so is it clear now? Okay. Okay, so now we'll move to the next question. So this is the question number 51 of GATE 2018 Metallurgical Engineering. Okay, so this will be 51, not 21. Okay. Hmm. So now the question is for the reactions of 4Ag in the solid form, and which is pure, is reacting with oxygen in the gaseous form, and it is forming 2 moles of Ag2O in the solid form and in the pure form. Okay. So now for this reaction, the standard enthalpy change is given, and also the standard entropy change is given. Okay. Uh, but remember, this is for the temperature range of this only. Okay. If the temperature range is below 298, or if it is below 298 or above 500, it will this values you cannot use. Okay. Now, it is asked that the temperature above which Ag2O decomposes in an atmosphere containing oxygen at a partial pressure of 0.3 atmosphere is. So, it is asking you the temperature at which or above which it will decompose in an atmosphere where oxygen partial pressure is 0.3 atmosphere, and the universal gas constant that is also given to you. Okay. So now we can see, or we can see from these reactions. So this is 4Ag, okay, solid, plus oxygen, the gas, is basically forming 2 moles of Ag2O in the solid form. So what will be the K for this reaction then? Equilibrium constant K we can write is K equilibrium we can write is So on the top it will be the activity of Ag2O whole square, and the bottom it will be the activity of Ag whole to the power 4, and here it will be partial pressure of oxygen. Okay, so now as both of these are in the pure form, so the activity of this will be 1 and activity of Ag will also be 1. Okay, so it will be 1 by 0.3. Okay, so now we have got the K equilibrium. Now what will be the delta G naught for this reaction? Delta G naught will be delta H naught minus T delta S naught, right? So now delta G naught is given directly given to us, but delta H naught and delta S naught is given. So that means we can write it as delta G naught is equal to minus 61080 plus 132.22 T. Okay, so this is your delta G naught for this reaction. Okay, so now we also know that delta G is basically delta G naught plus R3 ln K, right? Now at equilibrium your delta G is 0 and this will be K equilibrium. Okay, so that means you can write as ln K equilibrium is equal to minus delta G naught. So now you know the what is the ln K equilibrium. So sorry, RT. Okay, so R is given, that is 8.314 into T is not given, T we have to find out. Okay, and then ln of 1 by 0.3 is equal to minus of delta G naught, remember. So minus of delta G naught means it will be plus then 61080 minus 132.22 T. If you solve this equation, how much you are getting? Can you solve it and let me know? So I think we will get the T as, yes, we have solved it very quickly. So I think it will be 8.314 ln of 0.3 plus 132.22. Yes. So if you solve this one, you should get T is equal to 429 point something. How much it is coming? 429.4. Okay. So it has asked you what should be the temperature above which. Now if you go above this temperature, okay, if you go above this temperature, then like at this temperature it is at equilibrium. And if you go above this temperature, the decomposition of AgO2 will occur. Okay. So the answer will be 429.4 Kelvin. Okay, is it clear? Okay. Okay, so now let us move to the next question. So this is the question number 53 of GATE 2018 Metallurgical Engineering. The question is a 1 mole pieces of copper at 400 Kelvin is brought in contact with another 1 mole pieces of copper at 300 Kelvin and allowed to reach the thermal equilibrium. The entropic change for this process is in joule per Kelvin. You have to calculate the entropy change for this process. Okay, and the few values are given to, like the specific heat capacity of copper between 250 to 500 degree Kelvin. It is given. Uh, this is 22.6 joule per Kelvin per mole. So assume that the system containing the two pieces of copper remains isolated during this process. So it is told you to assume that two pieces of copper remains isolated during this process. It remains isolated means basically it is not mixing with each other or this kind of thing. Okay, so basically it was mentioned that initially you have copper one block of copper, let's say, and this is the second block of copper. So both are copper, but I'm drawing in different colors just to show the two different block of copper. So this was 1 mole, and this was also 1 mole. So it was having temperature at 400 Kelvin, and this second block was having temperature of 300 Kelvin. So now this initially these two blocks are separated with some kind of adiabatic wall or something. Let's say there was some adiabatic wall was there. That means heat transfer was not taking place. So now those two blocks of the copper are now kept in contact with each other. Okay. So that means now heat will transfer from this side to this side or from this side to this side. Okay. Whichever side is high temperature. Okay. So this is at high temperature. So from this side to this side, heat will transfer. So now what is the equation? So how you can calculate the equilibrium temperature for these two blocks? Initially it was 400 Kelvin and it was 300 Kelvin. So now we can calculate what will be the temperatures of these two blocks after when it reaches the thermal equilibrium. What will be the temperature? Yes, exactly. So heat gain is equal to heat loss. So for the first block, let's say this block I am writing as 1 and this block is 2. Okay. So first block heat gain will be N into Cp into dt. Okay. So N is 1 mole. Okay. Cp is given 22.6 to dt. So let's say this temperature now is T. So both will have same temperature as it is in thermal equilibrium at the equilibrium conditions. So now this block will release the heat. So this will be heat loss one. So this one, okay. So heat loss from this block will be uh, 400 minus T. Similarly, for heat gain for this block will be 1 into 22.6 into uh, sorry 300 minus T. Sorry, T minus 300. Okay, because it is heat gain. So if you calculate this, I think you should get it will be T will be how much? 350, right? T equilibrium or this T equilibrium. So now both of your block is at 300 Kelvin. Okay. Then it is asked to calculate the entropy change for this process. So if you consider one block separately, so this block is basically it is initially at 400 Kelvin and now it is at 350. And now it is at 350 Kelvin. Okay. And this block initially it was at 300 Kelvin and now it is at 350 Kelvin. So now what is the expression for your the thermal entropy? So delta S with temperature, how we can write? N into Cp into ln T2 by T1, right? Because you know, right, delta S is nothing but dH by T dt. DH by T. So now dH you know it is Cp Ncp dt by T. So if you integrate from T1 to T2, you should get it should be Ncp into ln of T2 by T1. Is it clear? Yes. So now, okay, I cannot. Okay. So now your one block is going from temperature 400 to 350. So for block 1 delta S1 you can write this as N is 1 mole, Cp is 22.6, it was 22.6, right? Yes, 22.6 into ln of T2 by T1. So T2 for this block is 350 and T1 is 400. This is delta S1 and delta S2 is for the block 2. So that for that case also it is 1 mole and your Cp is 22.6 into ln of T2 by T1. T2 for that block is 350 and T1 is 300. So now your total entropy change will be how much? Delta S1 plus delta S2. So that will be equal to 22.6 into ln of 350 by 400 plus ln of 350 by 300. So how much it is coming then? Can you calculate and let me know? How much you are getting? 0.46. Okay. Yes, it will be 0.466. So joule per Kelvin inverse. So the correct answer will be 0.466 joule per Kelvin inverse. So up to 3 decimal point you have to write it. So remember this one. Okay. So don't write up 0.46. Up to 3 decimal point it is mentioned. So you should write up to 3 decimal point. Okay. If this question is clear, then I will move to the next question. Okay. So this is the question number 25 of GATE 2018. The question is, a copper aluminum diffusion couple develops a certain concentration profile after an isothermal treatment of at 600 degrees centigrade for 10 hours. The time required to achieve the same concentration profile at 500 degrees centigrade is. So what will be the how to approach for this question? This is a very simple question. So basically, it is saying that at 600, you have one aluminum or copper diffusion couple. Okay. So let's say this side aluminum, this side copper. So after 10 hours, it develops some profile like it diffuses, aluminum diffuses and copper diffuses like this. Okay. Yes, exactly. DT is constant. So it is basically after 10 hours at 600 degrees centigrade. Let's say it is developing some kind of profile like this. Okay. So after at 600 degrees centigrade and 10 hours. Now it is asked that the same profile you want, but now at a temperature of 500 degrees centigrade. Okay. So for this, you there is simple relation is there. Tt, d is diffusivity and time is basically constant. You can also visualize this thing from the fixed seconds law, that is del c by del t is equal to d into del square c by del x square, right? So this is assumption is that d is not dependent on the concentration. That's why I kept the d outside. So now if you just rearrange this thing, you will get d into dt is equal to del c by del square c by del x square, something like this you will get. So if you see this side, uh, left hand side, it is d into dt. Now if you integrate, you will get dt, and this side if you integrate, you will get some expression. Okay, I'm not going into this. So so this side you can see it is totally dependent on the concentration and x. So now if the concentration profile is same, okay, so this side will be same for both the cases. So dt should be constant. Okay, now if the dt is constant, now the values are already given to you. So this is that's why as the values are given, so this make this problem very simple. Okay, so first case d is 4, sorry, at 600 your d is 8 into 10 to the power minus 13 into time is 10 hours is equal to 4 into 10 to the power minus 14, and time you have to calculate. So if you just calculate from this thing, you will get 80 by 4 into 10, that should come 200 hours. Okay, so now in these questions directly the, yes, you have calculated right, so it will be yes 200 hours. So now this question, the thing is that both the diffusivities are given to you at 600 and at 500. So both are given to you, but in some of the questions it may not the directly it may not give you the diffusivity at two different temperature. Okay, in the for those questions it may mention that at d at 600 is, let's say, 8.10 to the minus 3 13 meter square per second, and in case of d 500 you have to calculate, but in that case it will give you the q values, q something, q value will it will given like uh, any values, like it may be given, let's say 200 kilojoule per mole per kelvin, 200 joule per mole per kelvin, sorry, kilojoule per mole per kelvin. So this value will be let's say this q value will be given. Now if the q value is given, then how you will calculate the d at 500. So this is also similarly you can calculate like q and d not may be given, let's say. So if Q and D naught value is given, then using the Arrhenius equations, like yes, D is equal to D naught into exponential of minus Q by RT. So this way you can calculate the D at 500, putting the temperature at 500, 500 plus 273. Don't forget to convert it in the unit of Kelvin. Okay. So then you will get the D value at 500, and then you can calculate using these same methods. Okay. So this is this kind of question may be there, and another kind is like sometimes both may be given. So let's say this is a common statement for both question, one question and another question. It was given, calculate the activation energy for this. So how can you calculate the activation energy? Can you calculate the activation energy from this the given data? Is it possible? Is it d value is needed, or you can calculate? Okay, let us see if we can calculate or not. Okay, so your d at 500, it is d at 600. So 500 I'm writing first, and d at 600 it is given. Okay, so d at 500, how much it was? 4 into 10 to the power minus 14, right? And 8 into 10 to the power minus 13. Am I correct? Yeah. Okay, so now what is the Arrhenius equations? That is d into d naught exponential of minus q by rt. If you take ln both side, it will be ln d is equal to ln of d naught minus q by rt, right? Now for one equation you can write as ln d at 500 is equal to ln d naught minus q by rt. Q by r into t is 500 plus 273, and another equation will be d 600 is equal to ln d naught minus q by r 600 minus plus 273. Now if you take this equation 1 and equation 2, so if you just take minus, like 2 minus 1, if you do it, you'll get ln of d of 600 divided by d of 500 is equal to minus q by r 1 by 600 plus 273 minus 1 by, now you know the r value. Okay, you know d at 600, you know d at 500, so only unknown is q, right? So you can calculate q, and then you also can calculate d naught. So two equation, basically two equation, two unknown, right? So two equations, one and two, and two unknown. Two unknown is, one unknown is d naught and one unknown is q. So two equation, two unknown, you can easily calculate it. So you just put the values of d at 600 and d at 500, put the values of r, and then you can easily calculate the q. Okay, you can calculate in your home also, like how much you are getting, just for checking, and just for practicing also. Okay, so now I'll go to the next question. This is the question number 43 of GATE 2019 Metallurgical Engineering. The question is, equilibrium concentration of a dissolved nitrogen in weight percent rounded up to 3 decimal places. This, sometimes this part are very small thing, but you should notice this thing. Okay, in 3 decimal places, or sometimes it may mention it up to 2 decimal places. This thing you should be take care of. Otherwise, let's say if it is mentioned 3 decimal points, if you write up to 2 decimal point, then it might be a wrong thing. Okay, so better to write up to 3 decimal point and precisely, and then okay. So now this question is in pure liquid iron, you have dissolved equilibrium concentration of your dissolved nitrogen in pure liquid iron, which is exposed at atmospheric pressure at 1873. you have to calculate what is the dissolved nitrogen concentration at equilibrium for this temperature and for the atmospheric pressure or atmospheric conditions. Basically, it is exposed to atmospheric condition. So this is your some container where liquid iron is there. Okay, and this is your air basically, as it is exposed to atmospheric air. Okay, so uh, now you know Sievert's law. What is the Sievert's law? Can you tell me the Sievert's law? What is Sievert's law? Sievert's law is, yes, dissolved concentration of, let's say, nitrogen is basically K into partial pressure of nitrogen root over partial pressure of nitrogen. So this is your Sievert's law. Okay. Now how this law claims? This law claims nothing but like you have nitrogen in your air. So what it is doing? It is basically dissolving with your liquid iron in this form. Now if you write the equilibrium constant for this reaction, you will get uh, K equilibrium is equal to N whole square divided by partial pressure of N2. If you rearrange, you will get N is equal to root over of K equilibrium into partial pressure of N2. And now this K you can take it outside and let us term it as Kn and then root over partial pressure of N2. So this is your Sievert's law. Okay. So this is how your Sievert's law is basically it is coming. Okay. Now in this case Kn is given. So Kn is given through this reaction. Also temperature is given. Temperature is 1873. So if temperature is given, then you can calculate the Kn. So if you can calculate the Kn, then can you calculate the dissolved concentration of N? How can we calculate? So dissolved concentration of N is equal to nothing but your K of N into root over of partial pressure of N2. Okay. So now for this we need to know two things. One is Kn, that is already given, minus 513 by T, that is 1873, minus 1, how much it was? 1.063, right? 518, sorry, it is 518. So now log of Kn. So now can you tell me what how much value of Kn you are getting from this? Yes, 0.0457 or something like this. Okay, so this is the value of your Kn. Now you should know the partial pressure of nitrogen. What will be the partial pressure of nitrogen? Do you know the value of the partial pressure of nitrogen in this case? No, partial pressure of nitrogen is not one. This container is exposed in air. So the total pressure, this is your iron liquid. Okay, but, as it is in air, the total pressure, that P total is 1 atm. But partial pressure of nitrogen is not 1. Partial pressure of nitrogen is how much? Your air content around 21% of oxygen, around 78% of nitrogen, right? And the other 1% is some other elements, other gases are there. Okay, so now it contains 78% of nitrogen. So what will be the partial pressure of nitrogen? Mole fraction into your total pressure, it will be 0.78. Okay, so now Now you know the partial pressure of nitrogen. So is it clear why the partial pressure of nitrogen is 0.78 atmosphere? Yes. So in air basically contains 21 volume percent of your oxygen and 17 volume percent of your nitrogen. Okay, so that's why your partial pressure, that mole fraction will be 0.78. So mole fraction into total pressure, that is 1. So partial pressure of nitrogen is 0.78. So now if you can calculate, you will get 0.0457 into root over of partial pressure of nitrogen 0.78. So how much you are getting then? Yes, so 0.04 up to 3 decimal point. So 0.0404 means up to 3 decimal point, we can write it as 0.040. Okay, so the correct answer will be 0.040. So is it clear? Okay. Okay. So now let us move to the last question of today. So this is one question from the phase diagram. So this is the question number 8 of GATE 2018, metallurgical engineering. A 0.28% plain carbon steel sheet is heated and equilibrated in the intercritical region, followed by an instant water quenching. The microstructure of the quenched steel sheet consists of. So do you know what will be the answer? Can you how can we approach this one? It is very easy question by the way. So this if you know the phase diagram, so I am not drawing the whole part of this. Okay, so only up to the eutectoid region I am drawing. Okay, so this is alpha, this is gamma, this is alpha plus gamma, and this is gamma plus Fe3C. So it is mentioned that 0.28% of plain carbon steel. So this concentration is 0.8. So 0.2 will be in this region somewhere here, right? So that means in the hypoelectric region. So this is 0.2. So what treatment it is done? So it is heated and equilibrated in the intercritical region. So what does it mean by the intercritical region? Which region is the intercritical region? So let's say this somewhere it is a room temperature or something, and then it is up to the intercritical region. So intercritical region, does it means this up to this one, or this one, or somewhere between these two, or this one? This is, let's say, one, either this two region, or this three, or this four. Which location? Intercritical region. Yes, yes, exactly. So up to from this to this region anywhere. So from this, basically that means your initially basically it is heated to the alpha plus gamma, this phase boundaries, up to this phase boundary, this phase region. Okay, so here alpha plus gamma, so it is basically heated up to this one. So when it is heated this at this location, let's say this is location 1, I am marking. At location 1, what will be your microstructure? At location here 1, you have alpha and you have gamma. Okay, so mixture of alpha and gamma will be there. Now it is mentioned that after heating, it is followed by an instant water quenching. Now this is suddenly water quench. Now what will be your microstructure? Can you tell me what will be the microstructure? Yes, exactly. So at this point you have alpha and gamma. Alpha means this is the protectoid alpha or protectoid ferrite. Okay, and you have gamma. So but when you are suddenly quenching it, the gamma will transform to martensite. Okay, gamma will transform to martensite. Assuming that this temperature, this the MS temperature is lower than your this room temperature or the temperature of your water bath. So so gamma will transform to martensite. Okay, and as it is also a low carbon steel, so you can consider that all the gamma will transform into martensite. So it will form a microstructure of protectoid ferrite plus martensite. If it was a high means high carbon concentration is high, then maybe there may be some amount of lithium austenite may be there. Okay, so but as mentioned, as the option given in these questions, so the correct answer will be option B. So the final microstructure will have protected your alpha, okay, and your martensite. And let's say this is martensite, this martensite, okay. This will be the final microstructure. So is it clear to you? Okay, okay, okay. Okay, so then if you have any other doubts or anything, you can mail me anytime. Okay. So when is the gate exam? It is on 11th, right? Okay. Okay, then all the best for your gate exam. Prepare well and uh, give the exam very like carefully. Like don't make mistakes. So step by step, you just try to solve all the questions. If you face any difficulties or if you have any queries or any doubts, you can ask me anytime in the mail. I will try to answer. Okay. Okay then. Okay then I'll close the session for today. Okay. And all the best for your exam.